The question on the test before about like condensation nuclei versus ice nuclei. I just go find another question about that. Okay, so the test has a very similar distribution as far as what the materials were, and some of the questions there just wasn't another one. Okay, we'll do exactly the same question again or something like that. It's not that big of a deal, but that is how the test is framed. It's going to have almost exactly the same number of questions, etc., as it did before. All right, hopefully that will help straighten all that out, and it'll raise the average a few points, because maybe there were folks who, hey, I didn't think you'd ask about relative humidity or something. Well, now you know it's on there, so go study it. Definitely do not come in to retake the test cold. That would be a disaster. Okay, I mean, you don't come in thinking, hey, I took the test once before, now I know I don't need to study. No. Okay. All right, that would not work. All right, so. Today we're moving on into a new block of material that's more about the kinds of things you probably thought the course was going to be about. We're going to be starting to study the large-scale features of the atmosphere, the kinds of things that are influencing the weather that you are experiencing, things like fronts and jet streams and air masses and the general circulation of the atmosphere. And when I say that, I want to be clear about what we're talking about. When we talk about this term, general circulation, which is the topic of today's lecture, when we talk about general circulation, what we're really talking about is what the atmosphere is doing, what it is accomplishing, what kind of motions are happening in it, what is the large-scale motions of the atmosphere, what's happening in the atmosphere. This is very different than a term that you might have thought this was called climatology. In the textbook several times along the way has been using this word climatology. Climatology is about statistics. Climatology is saying the average temperature in Omaha on February 26th is 38 degrees Fahrenheit. It's statistics. And it's important, but that's not what we're doing here. What we're talking about when we talk about general circulation is why is the atmosphere doing what it's doing? Why is the atmosphere here relatively cool, whereas it's warmer to our south? Or why is the jet stream above us and not somewhere to our north? Or why are there cold fronts and warm fronts passing through our area and not passing through some other location? We're going to be talking about what the atmosphere is actually doing, what it's actually accomplishing today, and actually it takes us most of the next time too, on Tuesday. We're going to be talking about what the atmosphere is doing. We're not going to get bogged down in statistics like cold fronts come through Omaha an average of 5.8 times each February. Okay? That's not really where we're going with this. All right, so when we're talking about general circulation, we're talking about this large-scale system of motions in the atmosphere that are what the atmosphere is accomplishing. And the atmosphere has to accomplish something. There has to be some reason why the atmosphere is in motion. It's easier for it to not be in motion than to be in motion. So clearly there is some reason why the atmosphere is in motion. And fundamentally, this has been an important problem in the history of meteorology. Lots of big brains have tried to attack this problem of why the atmosphere is in motion. And what is it actually doing? And one of the first really serious attempts to take this on was done by Sir George Hadley. This is a long time ago, like 17th century. And Sir George Hadley was your fairly standard old dead white guy scientist. Okay? He's living in his manor house someplace in England. This is how science was done back then. They didn't actually go out and go out and take observations. They sat around and they stroked their beards while having coffee and brushing their golden retrievers. Okay? They just sat there and they thought about things. I don't know why I was thinking George Hadley had a golden retriever. Okay? He seems like the kind of guy who would. And Sir George Hadley thought about it and had a brandy over it and decided that, motions in the tropics are warm, so the tropics apparently have rising motion. I mean, we all know warm air rises. Right. Notice what I drew here. I drew rising motion in the tropics as like an arrow coming, like we're seeing the rising motion from the side. Oh my God, it's already visual, right? Here I'm drawing it, so like this is sort of the same motion as this, we're just seeing it from the other side, right? Okay? And it doesn't just happen like right here over West Africa and right here over the Pacific, it's happening everywhere around the globe where there's this rising motion. In meteorology and in physics for that matter too, when we want to draw an arrow coming out of the page, like the arrow that's rising right here over Ecuador, we draw it as a circle with a dot in the middle of it. A circle dot is like an arrow coming out of the page at you. So like all these are really arrows that are all showing the same thing. They're all showing air coming out, rising from the surface towards the top of the atmosphere. Right off the bat, oh my God, this is so visual. And Sir George Hadley also said, you know what, I know, I've never been to the poles, but I hear that it's cold there. So cold air sinks. So, because it's, you know, my ideal gas law, which he didn't know the ideal gas law, but he knew cold air sank. And, sank. So he's got air sinking at the poles. Notice again how we're drawing this. I mean, we're seeing it like from the side here. This is sinking motion. I know you're thinking, but it's up. No, but it's sinking if you were sitting here at the South Pole, right? This is sinking motion for you. And it's sinking motion at the North Pole. Sir George Hadley said, let's just connect the dots. Probably what's happening is air flows from north to south in the northern hemisphere. And that air that sank near the poles flows towards the equator. And that air that sank near the South Pole spreads north towards the equator. And we have winds. And we're down here at the surface, and we experience these winds. And then he said, you know what? Aloft, it's just a compensating circulation where aloft air flows from the air that rose near the equator, spreads out towards the pole, spreads out towards the pole. Something like this. And I could draw more arrows, you know, like air that rose here, goes towards the pole, but this starts getting pretty cluttered pretty fast. So I don't generally draw both winds at the surface and the winds aloft on the same plot. But just to kind of give you a sense. To give you a better sense, though, there's a nice diagram of how George Hadley thought it worked. And it's on your blue line page. Oops, let me go ahead and break this out of the blue line page. That's just a mess. Yes. 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 There we go. So George Hadley had this idea. Warm air near the tropics rises, cold air near the poles sink, and it just sort of makes these cells. This is a powerful vocabulary word, cell. When we talk about a cell in meteorology, what we're talking about is sort of a conveyor belt or a closed circulation. So see how there's like a cell where the air flows to the equator, rises, spreads out along the top of the atmosphere, sinks back down here by the poles. And Sir George Hadley thought this was how it worked. But Sir George Hadley had neither ever been to the tropics or to the poles. This was his idea. And it is not a bad idea, but it turns out to be wrong. There are a number of things that Sir George Hadley has wrong here. The most important is the fact that he didn't know anything about the Coriolis force. I mean, look at those arrows up there that are labeled surface flow. They've got wind blowing straight from the north to the south, all the way down to the equator. We know now, because, I don't know what his name was, Gustav or Anatov or something, Coriolis, discovered that motions in the atmosphere are deflected to the left in the northern hemisphere. I'm sorry, to the right in the northern hemisphere, the left in the southern hemisphere. You wouldn't really get the air to flow in a straight line like that. It would be deflected by the Coriolis force. Now, Coriolis lived like 300 years after Hadley. It's not really his fault that Hadley didn't know about that. But Hadley, on the other hand, should have realized, gee, when I sit up here in my manor house in England, it isn't like the winds are always from the north. Right? Which would be how this circulation pattern, these cells, seem like they should have been working. Right? It seems like sitting at the surface in England, he should have had winds from the north. Hey, let's be clear.